Hello and welcome. I'm Hossam Aly. I'm a postdoc at the Centre de Recherche Astrophysique de Lyon, CRAL. I'm going to be talking about dust traffic jams in inclined circumbinary disks. This is work that I've been doing with my collaborators listed here. This is within the Dustbusters collaboration, and all this work has been done with the SPH code Phantom. I'm going to give a bit of a background before. So a lot of work has been done on inclined circumbinary disks, primarily in the gas context. And the defining feature of this setup is that if you have a misaligned disk around a binary, the binary will exert a torque on the disk, and this will induce differential precession, so radially differential precession in the disk, leading to possible warping of the disk. Now, we know for gas disks from the work that's been done that this precession is around the binary angular momentum vector, and in the presence of dissipation, you will end with a co or counter aligned disk with the binary plane, and of course, if the disk is thin, then this torque will overcome viscosity, and you'll have tearing in the disk. And if the disk is thick, it will resist this tearing. This is more relevant for protoplanetary disks because disks are normally thicker. But then after some time, you will have, because the warp is communicated viscously, and you'll end up with a rigidly precessing disk around the binary until the final alignment. Now in 2015, we've extended that to see how that works for eccentric binaries. And the somehow surprising result was that the precession has a component around the eccentricity vector, not just the binary angular momentum vector. And that means is that for highly eccentric disks and bigger initial misalignments, you'll end up with polar alignment, not just co-alignment. Now, to just review what happens in the eccentric binary case. So if the figure on the left here is the precession trajectories with respect. So H here is the direction of the angular momentum vector of the binary. E is the direction of the eccentricity vector of the binary. And you see for a circular binary case, the top left one, that the precession of the angular momentum vector of the disk is circular around the binary angular momentum vector, and with the presence of dissipation, you end up with a co or counter aligned disk. But then when you increase the eccentricity for 0.3 or 0.6, you'll see these blue contours, and they are actually around the eccentricity vector. And the sort of phase space of this precession around the eccentricity vector increases with increasing eccentricity. And so for the 0.9 eccentricity case, you see that pretty much all misalignments that are higher than 10 degrees will end up in the polar alignment regime. And on the right here is just a comparison of the analytical model we came up with in comparison with the simulation. The agreement is very well indeed. But all of that was for just gas disks. Now, what happens to dust disks? So we had a look at this in a paper that was published earlier this year, Lyon 2020, and we explored a host of parameters ranging from very small to very large dust grains. But one of the things we found is that, of course, large dust grains that are not affected by drag, of course, they also don't feel pressure or viscosity, they will try to precess like test particles, so radially differential, whereas the gas will precess rigidly. And so you have both components precessing at different frequencies, and that depends on the radius. And of course, there's always going to be, because the dust precesses radially differentially, there's always going to be one radius in the disk where both the dust and gas precess at the same frequency. That only happens at one radius. So to show what I mean, this is on the left is the just the surface density profiles, and on the right is the twist profile. Solid lines are for the gas, and the dashed lines are for the dust. If you look at the right panel, you see that the gas precesses rigidly, so it's always straight lines, just one frequency throughout the whole disk, which changes with time. So the time goes from red is the initial condition, blue is the last snapshot. And you can see on the right as well that the twist profile for the dust is radially differential, and there's always one radius where both have the same frequencies. They both intersect each other at the same frequency, and you can see on the left that the density profile, there's a pileup at the inner edge of the dust disk. This is what we reported in the paper, but you can also see right at the last snapshots that there's another pileup that's starting to happen, that's starting to form. We didn't actually dwell on it very much in that paper, but we decided to go back and follow up on this, and so I tried to run the simulations for much longer, changing the disk parameters. We've tried a much wider disk to see what's how that behaves, and indeed you can see that there's a ring that forms just outside of the radius where both the dust and the gas precess at the same frequency. So the times here are much larger than the previous simulation. Indeed, the light blue one, which is the second snapshot here, corresponds to the final snapshot in the previous simulation. So as time goes, you have this very prominent ring that forms just outside of the co-precession radius. I'm going to a video of the simulation to show exactly what happens. I think if there's anything I'd like people to take home from this talk is this video. So gas will be on the left, dust on the right, and you will notice that the gas precesses rigidly, whereas the dust warps because it has different precession, different radii. In the beginning, there will be some ringing in the dust. That's just the dust settling. It dampens very quickly, and then you see the structures form. First the inner one, and then the outer one will take over. So without further ado, so you see the inner structure forms first, and then there's an outer one that forms as a spiral forms, and the density enhancement is actually quite significant. It's about an order of magnitude in terms of the dust surface density locally, and then after some time, this outer pileup will circularize and takes over. So this simulation, the lifetime of the simulation is around 300,000 years in total. And at the end, you are left with the dust disk is just these two rings, with the outer one much more prominent. There's a faint indication in the gas disk that there's a bit of a gap when the dust pile up, just because of the back reaction of the dust on the gas. So what actually is happening? what causes this this traffic jam, as you will. So if you have a co-precession radius where both the gas and the dust precess at the same frequency, then just inside and outside of this radius, the radial drift will be minimized, and that's just because of the projection of the dust orbital velocity on the gas plane, because the gas has just one plane, it precesses rigidly, it always has the same frequency. The reduction from this projection will match the reduction in the gas Keplerian velocity because of the pressure gradient. And so these two radii will minimize the radial drift because of the headwind experienced by the dust will be minimized. So in the beginning, of course, the inner one would form quicker. But then if you run the simulation for longer, the outer pileup will dominate, and that's just because it's closer to the mass reservoir, because radial drift is bringing dust particles from outside, and the outer radius is closer to that mass reservoir, and it causes a traffic jam. There's a poster by Cristiano Longorini that shows comparison of this analytical model with simulation results, and the agreement is pretty good. We've ran this simulation for a large range of binary and disk parameters, and we see it for both the circular and eccentric binaries, so both in the co-alignment regime and also in the polar alignment regime. And it happens whenever the initial inclination is higher than about 20 degrees, and for relatively large dust grains, so Stokes number higher than 50 or so. So to summarize, we see this dust density enhancement that's about an order of magnitude locally, because of this setup, and so the questions that we can ask is, does this traffic jam make planet formation more efficient in the context of inclined circumbinary disks? And I would say that's quite possible. But also one of the good things is that we can actually have a prediction of the radius that would preferentially form planetesimals and possibly planets in like inclined Tatooine planets. And I will stop here. Thank you very much.